Hello, hi everybody. I am Ram Mohan. I am working as head of department in Government Polytechnic, Mahbub Nagar. I am handling this subject basic electrical and electronics engineering. The topic we are dealing with is the inductors and transformers. The subtopic for the session discussion is the specifications of inductors and the inductors connected in series as well as parallel. Now let us see the objectives of this session. On the completion of the session, we'd be able to know the inductor specifications, then the inductance, total inductance when they are connected in series, and also the total inductance when they are connected in parallel. Well, let us recap what we have discussed so far regarding this topic. So on completion of this project, we know the inductor specifications, then the total inductance when they are connected in series as well as parallel. And then now let us recap. So we have so far discussed about the types of inductors. What are the different types of inductors based on the core material? Let us recall. So they are air core inductors, yes, iron core inductors, ferrite core inductors. Then again, based on the other factors also we have other classifications, that is on the frequency you have audio frequency coils and RF coils, though not mentioned here, we know that. Now let us see the main specification of the inductors. Number one is the inductance value, that is L value. Then it is the type of winding. Again, the another one is the internal resistance of the coil. Then there could be power rating to know how much maximum power it can withstand. Then we'll also have the temperature coefficient as the specifications. Then you have the core material, whether it is iron core or ferrite core or air core. Then it also depends on the frequency range where you want to use for. Then, do you know why the inductors are connected in series or parallel? First of all, is there any need that we should at all connect these things in either series or parallel? Yes, there will be some situations demanding us to make the connections as required depending on the design of the circuit. So here, let us see why actually there is a need for us to connect them in series or parallel. So they in the sense the inductors may be connected either in series or parallel in order to increase or decrease the total inductance depending upon the requirement of the circuit or the situation demand. Now let us see the series combination of the inductors. When the inductors are connected in series, the rate of change of current is same in all the inductors because same voltage, same current, and they are in series. So we know that when elements are in series, the current remains same in all the devices that are connected over there. And then so the rate of change of current is same in all the inductors. The frequency also of course remains same. And now let us see the other factor. So the total induced EMF is equal to the sum of the individual EMFs. That means suppose you have two inductors L1 and L2. The EMF induced in L1 will be different and naturally the EMF induced in the L2 will be different. So the total induced EMF will be equal to the algebraic sum of the two EMFs, individual EMFs. Now let us see when they are connected in series. So this is the case we are considering without any mutual inductance. That means we are assuming that there is no interaction of the fluxes between each other. So let us consider this. So now there are two inductors connected in series as shown in the figure, that is L1 and L2. The current I1 is flowing through both the inductors. The voltage E1 is dropping across the inductor L1 and E2 is the voltage that is dropping across the L2, and ES is the source or the signal voltage. That's the main apply to both the combinations. Now let the self-inductance of the coil L1 of the coil 1 be equal to L1, and similarly L2 be the inductance of the coil 2. And we have seen there in the figure that I is the current flowing through the coils, then Ls is the total inductance of the series combination. Now let us actually then try to derive an equation for the total equivalent inductance. Then now let us see what happens here in the circuit. The self-induced EMF in the coil 1 is expressed as E1, and that is equal to minus L1 di by dt. Similarly, we know the voltage induced in a coil is equal to L di by dt, and there is a minus, and because that EMF induced itself will be opposing the very current that is generating it or creating it. Now similarly, the self-induced EMF in the coil 2 is E2, and it is equal to minus L2 di by dt. Now in the series connection of inductors, the rate of change of current is same in all the inductors, and therefore the total induced EMF is equal to sum of individual EMFs of the coils. Now when you take ES is the total one, so that ES is equal to E1 plus E2, and that is equal to minus, you are taking out, so it is L di by dt plus L2 di by dt. So it will be minus L di by dt equal to minus L1 plus L2 di by dt. Minus and minus you are cancelling out, so di by dt also gets cancelled out. So the series inductance, total inductance of the circuit will be equal to Ls, and that is equal to L1 plus L2. So it's like resistors. When two inductors are connected in series, the total inductance of the combination will be equal to Ls, and that is equal to L1 plus L2. Now let us see further what. If there are n number of inductors that are connected in series, then the total inductance will be given by Ls. Ls stands for the series combination equivalent. So the total inductance will be equal to L1 plus L2 plus L3 plus so on until it is Ln. So when the inductors are connected in series without any mutual inductance, then the total inductance is the sum of their individual inductances, of course. Like you have seen above, it is Ls equal to L1 plus L2 plus L3 plus L4 up to Ln. Now let us see a small numerical problem on the derivation what we have done. So there are two inductors with an inductance values of 5 henries and 10 henries that are connected in series. Find the equivalent inductance of the combination. So the given data is L1 equal to 5, then L2 is equal to 10 henries, and Ls is the equivalent, that is expressed as L1 plus L2, and we know L1 is 5 and L2 is 10, so it is 5 plus 10, that is equal to 15 henries. Hence it is so simple that the total inductance of the combination series will be equal to 15 henries. Now let us consider the case where we have actually neglected the mutual inductance in the previous situation. Now let us also consider what happens if there is some mutual inductance, that is, there is some reaction or interaction between the two coils. In this case, the value of the total inductance will depend upon the amount of mutual inductance present and whether the combination is series aiding or series opposing. Okay, so it depends on the mutual inductance whether they are aiding or opposing. That also is important, how they are linked, the direction of the magnetic fluxes that are linking with each other's field. So it's the amount of mutual inductance, then whether combination is series or aiding opposing each other. Then let us consider the case of series aiding. In series aiding, the direction of the current through the two coils is such that their magnetic fields also aid each other. That means they also support each other. They rather sum up each other. So here you can see in the circuit below how they look like. So it's like north south and north south, the polarities. So they are supporting each other. That is how it is. And if you draw a common equivalent circuit for that representation, it will be looking like this. So you will be denoting the two coils with L1 and L2 values, and then the current, the left one coil is taken as coil A and the other one is taken as coil B. And the voltage here induced is E1 and E1 for A coil and E2 for B coil. The terminals are named as T1, T2 and T3, T4 respectively, as you can see how they are connected. Okay. Now let L1 be the self-inductance of the coil 1 and then L2 be the self-inductance of the coil 2 and then M is the mutual inductance between the two coils. I is the current flowing through the coils, then LSA. A is a notation we have added here because there is some mutual inductance factor, whereas LS is only for the series what we have just now discussed. So LSA is the total inductance of the series combination with some mutual inductance between the two coils. Then what happens? Let us see. The self-induced EMF in the coil 1 will be equal to E1 and it is expressed as minus L di by dt. So it is minus L1 di by dt. Then mutually induced EMF in the coil 1 due to current in coil 2 will be equal to E1 dash. So it will be equal to minus M into di by dt. Similarly, so this is mutually induced EMF in coil 1 due to coil 2 and vice versa also we should consider, of course. So the self-induced EMF in the coil 2 is equal to E2 and it is equal to minus L2 into di by dt. Then mutually induced EMF in the coil 2 due to the current in the coil 1 will be equal to E2 dash and that is equal to minus m into di by dt. Here the current is same, so it is almost equal both. Then the induced EMF will be equal to, total induced will be equal to sum of the individual EMFs. So we have to make the sum of all the EMF what we have expressed just now, that is E1, E1 dash, E2 and E2 dash. So yes will be equal to the algebraic sum of the individual EMF, that is E1 plus E1 dash plus E2 plus E2 dash. So if you substitute the expressions for each, we will be getting this equation. So it will be minus L1 into di by dt plus m into di by dt plus L2 into di by dt plus m into di by dt. So m into di by dt is common for both. So if you further do some transformations, you get getting as minus LA into di by dt equal to minus L1 plus L2 plus 2m into di by dt. So di by dt gets cancelled out. So the mutual inductance, so the equivalent inductance of the combinations with some mutual inductance will be expressed as equal to this. So it is LSA equal to L1 plus L2 plus 2 into M. So that is the mutual inductance getting doubled here. So in addition to the coil inductance individually, so you are getting 2M as extra factor when they are interacting with some linkages of flux. Now series opposing. So here actually we have seen it as series aiding. So you got it properly. Now this is in this case is next one, wherein the combination is in series, but they are in series, but the current direction is such that the two fields will be opposing each other. Now let us see this figure. So the two fields are opposing each other as you can see in the figure. So the north and south, again the south, there is south. So this is a problem because of some windings and all. We can control all these things. They are controllables. So these factors can be influenced or adjusted or controlled by us at the time of design. So the right hand side you can see that the circuit is drawn like that, wherein you can see the terminals where it is T1, T2 and where is T3 and T4. So they have been changed because you have to see that the field is opposing each other, and hence this connection will be valid as it is drawn on the right hand side in the circuit representations. Now let us see. E1 will be equal to minus L di by dt and E1 dash will be equal to M di by dt as we have done in the previous case. Similarly, E2 will be equal to minus L2 into di by dt. Again, E2 dash will be equal to M di by dt. Here actually we are not putting it as minus because they are opposing each other. So that is the reason why the symbol, the sign minus is not appearing over here. Hence the total equivalent EMF in the whole combination will be equal to the individual EMFs addition, and individual EMFs are E1 plus E1 dash plus E2 plus E2 dash. And here you see that, so as we have done it previously, but for that minus sign at both the E1 dash and E2 dash. Hence you are getting it as LSA stands for aiding, and now LSO is for opposing mutual inductance. So the expression for LSO will be equal to L1 plus L2 minus 2M. So this is a formula for calculating the total inductance of the combination when there is series opposing magnetic flux or the field is opposing each other. Now let us derive the formula for the mutual inductance. How to find out from these two? Now the value of the mutual inductance can be calculated using the formula M equal to LSA minus LSO divided by 4, where LSA is the total inductance when coils are seriously aiding, and LSO, as we have just done, will be the total inductance when both the coils are in series opposing to each other. So M will be equal to LSA minus LSO by 4, and that is the equation for that. Now let us summarize what we have discussed till now. The total inductance of the inductors connected in series without mutual inductance is given by Ls. So that is equal to L1 plus L2 plus L3 plus L4 so on till Ln, when there are n number of inductors that are in series. And the total inductance of the two inductors when they are connected in series aiding is given by LSA, wherein LSA is equal to L1 plus L2 plus 2M. Similarly, the total inductance of the inductors when they are connected in series opposing, that is given by LSO, that is equal to L1 plus L2 minus 2M. Now let us recall or check our memory with a small quiz. The equivalent inductance when the two inductors are connected in series is equal to choice A L1 equal to L1 plus L2, choice B 1 by L1 plus 1 by L2, then choice C it is L equal to L1 into L2, and choice D is none of the above. What's the right answer? It has to be L1 plus L2. Then next one. The two inductors with inductance value of 10 henries and 15 henries are connected in series. The equivalent inductance is 6H, 150H, 25H, and none of the above. What is the right answer? It is simply addition of both the individual values. So it will be 10 plus 15, so it will be 25. So the choice will be C. C will be the right answer. Okay. Now next one. Assuming there is no mutual coupling, the series inductance are added like A, the series resistance, then choice B is parallel resistances, then choice C is series capacitances, and choice D is parallel capacitances. How do they add up? Like in resistors or like in capacitors? So the mutual, when they are in series without any mutual coupling, then they simply add up like that of in the series resistances. The right answer is choice A. Right, it has become red, that is ticked by S. Now let us see some frequently asked questions in these topics what we have discussed so far. Number 1. List the important specifications of inductors. Then find the equivalent inductance when two inductors are connected in series aiding and also or series opposing. Now let us try some assignment questions so that we can work out at home for further understanding. Let us try comparing the series aiding inductors and also the series opposing. Okay, now let us hold on for this for the next. So we'll just take a pause for the next discussion, that will be the inductors in connected in parallel combination. Now let us continue with the with our next session, that is inductors connected in parallel. So the objectives to be fulfilled in this particular session will be like this. So we will be able to understand the total inductance when the inductors are connected in parallel. So this is our main objective for the session. Now let us recap what we have just now discussed in the previous session. If there are two inductors having inductances L1 and L2 that are connected in series aiding, then what is the resultant without considering the mutual inductance? Suppose if there is no mutual inductance, then it will be simply answer how much? L1 plus L2. And then in the above question, if the mutual inductance M is present, then what is the resultant inductance? So we know that it will be equal to L1 plus L2 plus 2M, that is in series aiding. And suppose they are series opposing, then it will be L1 plus L2 minus 2M. So this is what we have discussed and learned in the previous sessions. Now let us see the parallel combination of the inductors. When the inductors are connected in parallel, then the voltages across each inductor will remain the same as in the case of resistor. So the voltage there remains same, of course, and then the total current is equal to the sum of the currents through individual inductors separately. So it will be I1 plus I2. Now let us see here when they are connected in parallel without any mutual inductance. So as we have considered the case of series also, here we are not considering the mutual inductance factor. Consider there are two inductors having inductances L1 and L2 connected in parallel across a voltage source EP as shown in the figure below. So this figure. So it will be EP is the voltage applied across parallel combination of L1 and L2, and I1 I2 are the respective current flowing through each inductor. Let L1 be the self-inductance of the coil 1, and similarly L2 be the self-inductance of coil 2, then LP be the total inductance of the parallel combination. Then the self-induced EMF in the coil 1 will be equal to E1, and it is like we know it, minus L1 into di1 by dt. Here it is not di because the current is different in both the coils. So here the EMF induced in the first coil E1 equal to minus L1 into di by dt, and the self-induced EMF in the coil 2 is E2, that is equal to minus L di2 by dt. Then when two or more inductors are connected in parallel, the same voltage is induced in each of them. So the total current change must be equal to the sum of the individual current changes. Therefore, total I will be equal to I1 plus I2, and then di will be equal to di2 di1 plus di2 by replacing, but E is equal to LP, what we have just now done, LP into di by dt, that is equal to L1 di by dt, that is equal to L2 di by dt. we are talking of the voltage, so they have to be same. Therefore E into E dt. So here we know that because the voltage has to be same across each coil, so we are trying this equation. LP will be equal to di by dt, and L1 will be equal to di1 by dt, and L2 will be equal to di2 by dt. So E into dt by LP equal to E into dt by L1 plus E into dt by L2. Therefore 1 by LP equal to 1 by L1 plus 1 by L2. So this is the derivation we will be getting for the equivalent. So how does this represent, or is it able to recalling anything? So we remember that this is the similar equation for the resistors in parallel. So 1 by R equivalent to 1 by R1 plus 1 by R2. So similarly for inductors it is same without any mutual inductance. And if there are n number of inductors connected in parallel, then the total inductance will be given by 1 by Lp equal to 1 by L1 plus 1 by L2 plus 1 by L3 plus 1 by L4 plus so on till 1 by Ln. Now let us see some problem on the inductors connected in parallel. So let us consider a problem when there are two inductors connected in series having values of 10 henries and 15 henries each when they are connected in parallel. So find the equivalent of the inductance of the combination. Now how to do it? Just we did it for parallel resistors, it will be on the same lines of data. So here the given data is L1 equal to 10 henries, L2 is equal to 15 henries. So as per our derivation, it will be 1 by Lp equal to 1 by L1 plus 1 by L2. So parallel equivalent will be equal to 1 by L2 plus L1. So it is 1 by 10 plus 1 by 15. So that will give an answer of 6 henries. So it will be like 15 plus 10 divided by 15 into 10. That's all. 30. So it will be 6. So the parallel combination is going to give us a equivalent resistance, inductance of 6 henries. Now let us do this one more derivation based on the. So this is the equivalence of inductance when they are connected in parallel with some mutual inductance. So the total inductance of the two coils connected in parallel with mutual inductance is given by L equivalent L equal to L1 into L2 minus M square whole divided by L1 plus L2 minus 2M for the parallel aiding, and so it is L equal to L1 into L2 minus M square whole divided by L1 plus L2 minus 2M for parallel aiding. So for aiding it will be minus 2M. This we should remember. And again for the parallel opposing it will be L equal to L1 into L2 minus M square divided by L1 plus L2 plus 2M. So this is for parallel opposing. Now let us summarize the things what we have discussed so far. The total inductance of the inductors connected in parallel without mutual inductance is given by 1 by Lp equal to 1 by L1 plus 1 by L2 plus 1 by L3 so on for 1 by Ln. And similarly for the total inductance of the inductors when they are connected in parallel with some mutual inductance. So the expression for them will be equal to L, that is equal to L1 into L2 L1 into L2 minus m square divided by L1 plus L2 minus 2m. This is for aiding fluxes. Similarly, for opposing fluxes, it will be L equal to L1 into L2 minus m square whole divided by L1 plus L2 plus 2m. This is for the opposing fluxes when they are connected in parallel combination. Now let us recall or check our memory with a small quiz here. The total inductance of the inductance of the two coils when they are connected in parallel for aiding fluxes is, aiding means it has to be minus. So the choice A is L equal to L1 into L2 minus m square divided by L1 plus L2 minus 2m. Then choice 2 is L equal to L1 into L2 minus m divided by L1 plus L2 minus 2m. Then C equal to L equal to L1 into L2 minus m square divided by L1 plus L2 minus m. Choice D, L equal to L1 into L2 minus m whole divided by L1 plus L2 minus 2m. What could be the right answer? Because L1 plus L2 minus m, single m is not there, we know it. It should be 2m for two inductors. So C and D are ruled out. And what is it written here for? Two aiding fluxes. So that has to be minus 2m. And we know it has to be m square. So the choice is A. So L equal to L1 into L2 minus m square divided by L1 plus L2 minus 2m is our right answer. The next one. The total inductance of the two coils when connected in parallel for opposing fluxes will be equal to choice A. L equal to L1 L2 minus m square it is given as product into L1 plus L2 plus 2m. Here between the two brackets there has to be a divisor or a slash to indicate that they are actually in the denominator. That's a small mistake over there. So just treat it as L equal to L1 plus L2 minus m or m square whatever divided by L1 plus L0 plus m. And likewise. So L's choice C will be equal to L1 into L2 plus m divided by L1 plus L0 into m. Then choice D is none of the above. What is the right answer? It is the choice A. So it is A, L equal to L1 into L2 plus m square divided by L1 plus L2 plus 2m. So let us look at the next one. So this is to know about some frequently asked questions in the topics we have just now discussed. So first one, write expressions for the total inductance of two coils connected in parallel aiding. A, that is parallel leading, then B, parallel opposing. Next one, derive an expression for the total inductance of two coils connected in parallel without mutual inductance. So they are connected in parallel without any mutual inductance. Yes. Next, let us have some assignment sort of questions. Write the expressions for total inductance of the two inductors when they are connected in number 1 parallel aiding, and then number 2 is parallel opposing. So these are few assignment sort of things what we can work out at home. And here let us also discuss about some, I mean, the applications and uses in the next sessions regarding the inductors. So with this, we'll stop here, and thank you very much for being here. Thank you very much.